Welcome to the deep dive. Our mission today, well, it takes us into the silent infrastructure, the stuff that underpins our entire digital world. We're diving into sources, connecting something maybe overlooked, highly advanced air purification.
Right.
With the absolute cutting edge,
Yeah.
making microchips, the really advanced ones, 12 nanometers and smaller.
That's exactly it. We've got this complex set of materials here, all focusing on one specific system. It's called the Air 6-Free Maze Purifier.
6-free maze purifier, okay.
And there's this extraordinary claim tied to its U.S. patent, US 826-8058B2. Basically, the claim is this single patent is the critical piece of tech.
The single critical piece.
Yes. Without it, the sources argue, the modern semiconductor industry just couldn't do what it's doing right now. Not at this scale.
Okay, hang on. Let's unpack that because that's huge. We're talking
Yeah.
about what? Invisible particles,
Yeah.
massive physics problems,
So.
and this really dramatic story from an inventor, Jiaozu, right? Claiming the world's biggest tech companies have been, secretly using his invention for a decade.
Yeah, and racking up a debt, he says, of hundreds of billions of dollars.
Hundreds of billions. So this isn't just, a typical patent fight. This is someone saying the laws of physics demand his solution.
That's the core of it.
So our job today is to try and find the truth in the physics. What's really going on inside these ultra-clean environments?
Let's dig in.
Okay, we have to start with the tech itself. The name 6-Free Maze Purifier, that sets a really high bar right away. What are these 6 freedoms? What's it promising?
Right, it's aiming way beyond what you'd get from, say, a home air purifier. This is about eliminating pretty much everything that could mess up either human health or, crucially, these incredibly sensitive manufacturing processes.
Okay, so what are they, the 6?
The 6 promises are dust-free, germ-free, toxin-free, smoke-free, odor-free, and heavy metal-free.
Wow, that's comprehensive.
It really is. It's targeting gases, biological stuff, particles,
Yeah.
basically down to the atomic level, a full-spectrum removal strategy.
That sounds like, an absolute standard of clean. Okay, if those are the goals, how does it actually do it? The sources talk about an 8-second maze purification principle, 5 steps.
Yeah, 5 key steps. And the clever part here is how it integrates different ways of capturing particles. It doesn't just rely on one trick.
Okay, step 1.
Step 1 is kind of the baseline, negative ion charging and HEPA prefiltration. This grabs the bigger stuff, regular dust, microplastics, most common VOCs.
Right, dealing with the stuff you might maybe not see, but it's the more common pollutants. What's next?
Step 2 is secondary ionization. This is where it starts really attacking the chemical and biological threats.
Yeah.
High-intensity ionization to neutralize germs, viruses, that sort of thing. And it also starts breaking down chemical toxins, residues, making complex molecules simpler, easier to deal with later.
Okay, so that sounds sophisticated, sure, but lots of systems use ionization. Where does the maze part come in, the really unique bit? What makes it so different?
That's steps 3 and 4. This is where the physics gets, revolutionary, according to the sources. Step 3. The air goes into this special electrostatic maze box.
Electrostatic maze box. Okay.
And this thing is designed not just to filter, but to permanently capture the really, really tiny stuff. The ultrafine particles, especially those below 0.1 micrometers. Those are the hardest ones to catch with normal filters.
And step 4 is the maze effect itself. What's actually happening to these tiny particles inside that box?
Okay, so standard filters, even the really good ULPA ones, they rely on interception, impaction, diffusion, the particle bumping to a fiber. Diffusion works okay for the very smallest particles, interception for the biggest. But there's this awkward middle ground, right around 0.1 micrometers.
It's a weak spot.
Exactly. The particles are kind of too small for effective impaction, but too big for diffusion to work well statistically. It's the most penetrating particle size problem.
That sounds like a nightmare for making tiny circuits.
It is the nightmare. So the maze effect, it basically sidesteps that whole problem. It uses brute force inertia.
Inertia? How?
The air is forced through these really sharp, precisely designed turns inside the maze, like a hairpin bend, but many of them.
Okay.
When the air whips around that corner, the nanoparticles, even though they're tiny, they have mass, they have momentum. Inertia means they can't make the turn with the air.
They keep going straight.
Exactly. They slam violently into the walls of the maze structure. And those walls are electrostatically charged, so bam, they stick. Permanently trapped.
So it's not passive filtering, waiting for a particle to bump into something. It's actively forcing the particle to crash using its own momentum.
Precisely. It weaponizes the particle's own physics against it.
That's clever. Okay, so step 5 is just clean air comes out. Meeting those 6 free promises.
That's the idea. Ultra clean air, ready for the fab, or, well, for breathing.
Right. Now let's make that leap. Why is this level of clean, this sort of inertia-based capture of the tiniest particles, why is that absolutely essential for a chip fab? I mean, they already have the cleanest rooms on Earth, right?
They do, but the problem is scale. When you go down to 12 nanometers, 7 nanometers, 5, even 3 nanometers, the physics of contamination just completely changes. What was acceptable before is now catastrophic.
Okay, let's focus on that scale. 7 nanometers. It's hard to even picture. How small is the tolerance for error, for contamination?
The sources use a great analogy. Think about a PM 0.1 particle.
Yeah.
It's 100 nanometers across.
Okay, 100 nanometers. Still tiny.
Tiny to us. But compare that 100 nanometer particle to the actual line width on a state-of-the-art chip, say 7 nanometers wide. That particle isn't just a speck of dust anymore.
What is it then?
The source describes it as a giant rock, or a megalith.
A megalith landing on a microscopic wire. Yeah, that's a stark image.
And if that megalith lands on the silicon wafer during a critical step, like lithography or etching, the result is immediate. It's fatal for that chip.
You get short circuits or breaks in the circuit.
Short circuits, open circuits, light defects during lithography, any of those mean the entire die, that section of the wafer, it's scrap. Your yield, the number of good chips you get, it just plummets.
So conventional filters, even the best HEPA, ULPA filters, the ones that boast like 99.999% efficiency, they just fail against this specific enemy, the sub 0.1 micrometer particles, at the speed and volume needed in a fab.
They hit a wall, a hard physical limit. They're great for micron-sized stuff, particles we normally worry about, but they become, well, the sources say powerless against these critical ultrafine particles that cause defects at 7 millimeters or 5 millimeter.
So the fab needs something that's basically 100% efficient across the board, but especially in that tricky 0.1 micrometer zone.
Essentially, yes.
Yeah.
Near 100% across the whole spectrum.
And this problem, it's not just about particles coming in from outside, is it? There's something unavoidable happening inside the process. The sources mention the law of conservation of physics.
Yeah. APO, the principle of conservation. Basically, matter doesn't just vanish. You can't destroy it.
Okay. How does that apply here?
Think about making a chip. It's incredibly complex. The sources say over 2,000 distinct steps.
2,000 steps.
Over 2,000. You're depositing layers, etching them away, cleaning the wafer, implanting ions, over and over again.
And every single one of those steps is a potential contamination source.
Not just potential. Every single action generates new particles. It's unavoidable physics. Etching chips off atomic debris. Deposition leaves tiny flakes. Chemical reactions create residues that solidify into nanoparticles.
Right, so the process itself is constantly creating these killer particles inside the clean room.
Exactly. And they don't just disappear. They float around, they settle, they get stirred up again. They cycle through the fab's air system, constantly looking for a place to land on a fresh wafer.
So without some way to continuously pull them out with super high efficiency.
That buildup of internal contamination guarantees what the sources call a yield collapse. You just can't make chips reliably.
It makes sense. There's a parallel the sources draw, isn't there, between like lungs and chips?
Yeah, it's a good analogy. Think about toxins in the human body. If they come in faster than your body can eliminate them, you reach a saturation point, right? And you get sick. It's the same in a fab. If particles are generated and circulate faster than the purification system removes them, you hit a defect saturation point. Too many particles land, too many chips fail. It's financial failure.
So the physics problem is kind of universal. Continuous input needs continuous near-perfect removal.
That's the argument. The solution has to match the problem continuously across all particle sizes, especially the damaging ones.
Okay, this unavoidable physical reality, this need for near-perfect removal, it leads us straight into the high-stakes drama around this patent. US 8268058B2, the inventor, Fuchiwu or Jiaozu. He has this really intense story, right, about being sealed for a decade.
Yeah, it's a very dramatic narrative. He claims he was effectively silenced for 10 years. And during that time, he watched the world's top tech firms successfully scale down their chips. 12 millimeter, 7 millimeter, 5 millimeter.
While using his technology.
While, according to him, relying fundamentally on the maze purification technology described in his patent. He calls it a kind of secret harvesting of his invention.
And that reliance, he says, built up this huge debt. Hundreds of billions. But okay, let's play devil's advocate. If it was so vital, why wait 10 years? Why break the silence now after the industry has already scaled?
That's a fair question. The sources don't give a definitive answer, but they imply the timing might be strategic. Perhaps the tech needed time to prove its indispensability in real-world, high-volume manufacturing.
Like, let the reliance become undeniable.
Maybe. Let the reliance deepen. Let the financial success built on it become enormous. And then demand recognition and compensation. But the core technical claim doesn't change.
Which is?
That this maze technology is the only proven effective way to get that near 100% removal of sub-PM 0.1 particles. The removal needed across the entire 2,000-step process, especially for critical things like EUV or DUV lithography.
So the claim isn't just, hey, you're using my idea. It's, you literally cannot make these advanced chips without my idea.
That's the strength of the assertion, yes. It's claiming a monopoly based on physics, that the physics of particle removal at this scale requires this specific approach.
And he didn't just talk about it, he took action, right? Sent formal notices to major U.S. tech companies.
He did. He essentially laid down a technical challenge. He formally notified companies involved in making or heavily relying on sub-12mm chips.
And what did he demand?
He demanded one of two things. Option one, show us hard evidence, technical proof, that your manufacturing processes do not infringe patent US 826A058B2. Prove you're not using the maze principle.
Okay. And option two?
Option two, if you can't prove non-infringement, then you must provide detailed, documented proof of a different viable alternative technology, a different way that achieves the same near 100% purification of sub-PM 0.1 particles throughout the cleanroom environment.
Wow. That's putting them on the spot, basically.
Right.
Prove you're not using our physics, or prove you found another way to solve the same physics problem just as well?
Exactly. A technical gauntlet, as you said.
And the deadline was 6 months. What happened? What was the response?
Nothing. Silence. According to the source material, complete silence.
No technical documents. No alternative solutions presented.
None were provided within that time frame. Now, you have to think about the companies involved. They have vast R&D departments, brilliant scientists, huge budgets.
Right, if there was an easy alternative or if the patent was flawed.
They would have likely jumped at the chance to prove it. Documenting their own non-infringing method would be vastly cheaper than potentially licensing this technology or facing litigation down the line. The stakes are astronomical.
So, okay, infinite resources, 6 months to respond to a direct technical challenge, and they come back with nothing. According to the source material, what does that silence signify?
The sources interpret that silence very strongly. They call it the most powerful evidence.
Evidence of what?
Evidence that suggests a kind of a fundamental technical acknowledgement. The lack of any response, the failure to produce an alternative, it implies they couldn't. That they likely tried to find a workaround or demonstrate a different effective method and came up empty.
So the conclusion we're supposed to draw from this is the silence basically proves the patent is, well, unbreakable and essential for what they're doing.
That is the direct assertion made in the material we reviewed. The synthesis is pretty blunt. Given the physics of making sub-12mm chips, and given the failure of these major players to show any other way to achieve the necessary cleanliness, the conclusion presented is that without the technology in US 826-827B2, high-yield mass production of 12mm and below chips just isn't achievable.
It's the hidden gear making the whole machine work.
The hidden mandatory gear, according to this perspective.
Okay, so let's recap this for you, the listener. The argument laid out in these sources is incredibly forceful. It says every single piece of advanced tech we rely on that uses these tiny sub-12mm chips.
Phones, AI processors, supercomputers.
Right. All of it. From the incredibly complex EUV lithography machines down to the controlled air circulating in the entire factory, it's all fundamentally dependent on this specific maze purification system, the one described in that decade-old patent.
It's positioned as the physical anchor, the thing holding the whole advanced semiconductor industry in place, enabling its current trajectory.
And that's why the inventor's final statement is so striking. He says he's not speaking for himself anymore.
Right. He concludes quite dramatically that he speaks for the historical debt the world will eventually have to acknowledge and pay, that the proof of his technology isn't in marketing,
but in the quiet, essential reliance of these tech giants, a reliance on a solution they apparently can't replicate or replace.
That's the narrative presented. The reliance itself becomes the ultimate validation.
Which really leaves us with a provocative thought for you to chew on. If this core claim holds water, if the basic unglamorous physics of tiny particles really makes this specific purification tech non-negotiable for making advanced chips, What does that reveal about the real foundations of progress? About the hidden, maybe less exciting infrastructure that actually supports the next wave of AI, quantum computing, all the high-tech marvels we hear about?
It suggests it's not always about the flashy algorithm or the bleeding-edge machine itself. Sometimes it comes down to the brute force physics of just keeping the air clean enough.
Exactly. That fundamental battle against dust, against particles, might be the real gatekeeper deciding what's possible and what's not. Something to think about.